In this section, let's discuss about stack memory. Stack memory is part of the main memory. The main memory could be internal RAM or it could be external RAM. The stack memory is mainly reserved for the purpose of temporary storage of data, what we call as transient data. Stack memory is mainly consumed during function or interrupt exception handling. Stack memory is accessed in a last in, first out fashion, that is LIFO fashion. The stack can be accessed using push and pop instructions or using any memory manipulation instructions such as load or store. Most of the processor architecture supports using a dedicated instruction such as push and pop in order to manipulate stack memory. The stack is traced using stack pointer register. So most of the processor architecture carry a special register called stack pointer register. And that stack pointer register is used to trace the consumption of stack memory. When you use push and pop instructions, those instructions directly affect stack pointer register. That means they can increment or decrement the stack pointer register values. In ARM Cortex-MX processor, the register R13 is considered as SP, that is stack pointer register. Let's move forward. Why stack is used? What are the uses of stack memory? Now, the stack memory is mainly used for temporary storage of processor register values. It can be used for temporary storage of local variables of the function. When you write a C function and when you create a local variable, then the memory for that local variable will be reserved in stack memory. And when that function exits, those memory will be reclaimed or deleted. That's why stack memory dynamically expands and shrinks during runtime of the program. During system exception or interrupt, stack memory will be used to save the context of the currently executing code. Context of a currently executing code is nothing but collection of some general purpose registers, processor status register, and the return address. All this information will be temporarily stored in stack memory in order to handle the interrupt or the exception. So we'll understand more on this as we make a progress. Let's move forward. I said one thing, that is stack is part of RAM. If you consider our microcontroller has a RAM that is also called as SRAM. In our microcontroller, that is STM32F407 microcontroller, we have two SRAMs, SRAM1 plus SRAM2. Collectively, we can call it as SRAM, and its size is 128 kilobytes. We have 128 kilobytes of SRAM on our microcontroller. If you are using some other microcontroller, a different one, or if it is from different families such as F1X, F0X, LX, then there could be some differences. You have to refer to the data sheet or reference manual of the microcontroller. In this figure, you can see that the RAM is divided into three parts. If we consider this as a start of RAM and consider this as end of RAM, this part is reserved for stack memory. Another part of the RAM can be reserved for heap, and the rest of the RAM can be reserved for global data storage. When do you use this part? Let's understand each part. This part, we can call it as global data section. This part of the RAM will be utilized when the program contains global data and static local variables. When you have lots of global data in your program, then those global data will be stored in this part of the RAM. Your program can read write into this RAM location. Even you can store instructions here and execute it. You can even use this as a program memory. Another part of the RAM can be used for heap. That is, it will be utilized during dynamic memory allocation. Let's say in your program you use malloc or free APIs, the dynamic memory allocation APIs from the standard library. Those libraries reserve the space or memory from this part of the RAM. You have to inform the standard library or compiler which part of the RAM you want to reserve for heap or stack or global data. That settings you have to do in your toolchain or from your linker scripts. So we'll see that later, don't worry. If you are not using any standard library dynamic memory allocation APIs, then you can write your own dynamic memory allocation APIs, and you can write in such a way that it can reserve the memory from this part of the RAM. That's for dynamic memory allocation. This section or part of the RAM can be used for stack. So this will be utilized during function call to save temporary data, temporary storage of local variables of the function, temporary storage of stack frames during interrupts and exceptions. In all those cases, this part of the RAM will be utilized, which is nothing but stack. You may be having one question: who decides these boundaries? As I said, it is decided by you. You have to do some settings in your program or in your toolchain or in the linker script in order to decide these boundaries. It is completely depending on your project. I can even move stack at the front and global data section at the back. I can shift this heap area to somewhere else in the RAM. I can even do that. This is just one example. Stack operation model. In this section, we are interested in understanding stack. That's why let's understand stack operation model. In Cortex-MX processor, stack consumption model or stack operation model is full descending. Let me explain that. There are different stack operation models such as full ascending stack, full descending stack, empty ascending stack, and empty descending stack. Out of all these four, ARM Cortex-MX processors use full descending stack operation model, and we are going to understand that next. In the next lecture, I'm going to explain different stack model operation. I'll see you in the next lecture.